Hi, my name is Andrew Psaltis. The talk's going to be about going deep with Spark streaming. It's kind of an outline of kind of where I want to take this talk. Go through introduction, talk about DStreams, which is a fundamental component of Spark streaming, talk about how we think about time in streaming, go over a little bit about recovery and fault tolerance, and then conclude and have questions. Quick little bit about myself. I'm a data engineer at Shutterstock. Outside of Shutterstock, sometimes ramble on Twitter, not often. Author of Streaming Data. I started dreaming about streaming since about 2008 and working with streaming systems. Speaking, provide content for Skillsoft, and outside of that, I live in a lacrosse-crazed family. So why streaming? This is a great quote from Dana Sandhu that without stream processing, there's no big data and no Internet of Things. It's really kind of interesting that this is a little device from Texas Instruments called a Smart Tag. It's got 10 different sensors. So everything from mic, temperature, accelerometer, all sorts of movement. So 10 of them in here. $29, 29 US dollars for this little device. A little chip, if you will. If you haven't heard enough cases this last day and a half as to why streaming, here's a couple more. Operational efficiency. 1 extra mile an hour on a locomotive on its daily route can save $200 million in US dollars, and that's from Norfolk Southern. And it's not that it can't get the locomotives to go fast enough, it's the logistics of getting them in and out of the yard and routing them. From the EU Commission, congestion accounts for about 100 billion euros, or 1% of EU GDP annually. So improving these things with streaming systems becomes not just advertising, but real money. So I think we have a shared problem here. Today, if a byte of data was a gallon of water, we could fill an average house in 10 seconds. By about 2020, it'll take only 2. So the goal of this talk is to really kind of go through how perhaps Spark streaming could help us solve this problem. And this is only going to continue to grow. And it's not the data that we're producing, browsing the web or doing social things, but stuff like this that's everywhere and becoming more pervasive. So if you haven't used Spark streaming, just kind of quick little background on it. So this is the typical stack you see with Spark. Spark streaming just being one component of it. Provides an efficient, fault-tolerant, stateful stream processing. Provides a simple API. Integrates with Spark's batch processing and the other libraries. Okay, so you could use MLlib, you could use GraphX, you could use Spark SQL along with Spark streaming. Today we're just going to focus on Spark streaming. This is a high-level architecture of how it all works. So on the far left, you have your program that's running. It's a driver, no different than a regular Spark program. It gets sent out to the workers, and that's where your algorithm runs and your streaming job is running. And then you have data sources that are coming as input. Okay, those could be anything from Twitter, a tag, a device, a network, whatever it is you want to consume data from. So DStreams, discretized streams, it's the basic abstraction provided by Spark streaming. And the way it pretty much works, the way you look at it is, if this is time going across, it really is just little micro batches of RDDs being generated as time is progressing. Okay? There's 3 things that we want to do with them, and this is really similar to the 3 things we're going to do with almost any data processing system, right? We want to be able to ingest data, we want to do some sort of transformation or something on it, and then we're going to want to output it somewhere to something. Ingestion of DStreams, there's 3 ways you can get data in. There's basic sources, advanced sources, and there's custom sources. The basic sources are things that are built into Spark streaming. Come with it, there's nothing you have to include. And it's things like the file system, network socket, Akka actors. Stuff that's not built in, but is available, is things like Avro and CSV. And there's a Spark projects site out there that you can find other libraries. One thing to note about the basic sources is they're not reliable. Right? If you think about it, a file system or reading a file or off of a socket, it's probably not a reliable operation. The advanced input streams, on the other hand, are things like Twitter, Kafka, Flume, Kinesis, MQTT, or other protocols that you may see. Those all require an external library. Not really a big deal, but just something to be aware of that you'll have to get a library for that. It's not part of the core Spark package. And depending upon the source, these could be either reliable or unreliable. And we'll go over the difference between them and how you could do each one. And then there's custom input streams. To implement a custom input stream, you really just have two things to do. You have to input an input DStream, and you have to implement a receiver. Putting together a custom input stream is pretty much as simple as this. You would extend this receiver input stream. You have one method to get receiver, and you're going to return back the receiver. And that's really it. The receiver side of it is a little bit more work involved. In this case, you extend receiver. There's an onStart method, which has to be non-blocking. Okay, this is going to get called when it gets pushed to your workers, when it starts. There's a stop method, an onStop, clean everything up. And then there's a store method. Okay, and that's defined in the receiver class. In that store method is where you have decisions about reliability, unreliability. All right, kind of where the rubber meets the road as to what you're going to do. So let's talk a little bit about the receiver reliabilities. As we mentioned, there's unreliable and reliable receivers. Unreliable, pretty simple to implement, no fault tolerance, but you're going to lose data whenever the receiver fails. All right, you pretty much just consume it, you lose messages, you go on. But pretty simple to get up and running. Right? You're going to consume data from a file, from a network socket, really simple. The reliable receiver, on the other hand, complexity could depend on the source. Right? It depends on where you're going to try and read that data from, what you need to do. It could have strong fault tolerance guarantees, so you could have zero data loss. But the data source must also support acknowledgement to have that. Okay, so if you have a data source that does not support acknowledgement, you're going to have trouble having this fault tolerance and zero data loss. It's kind of a walkthrough of when you have a DStream, input DStream in a receiver, whether it's a custom one or whether it's one of the built-in ones, of how this kind of works. So when you submit your job to the master, it's going to go ahead and get call that get receiver on your input DStream. It's then going to turn around and send it to the Spark workers. So one thing to note, right, which is probably potentially obvious here, is that when it does send it, that receiver has to be serializable, right? That's going across the network to this other machine. So it's going to send this receiver. Your receiver is going to start running. It's going to consume data from whatever your data source may be. It's going to call a store method that we saw, right? That's going to store the blocks. Potentially going to replicate the blocks to other nodes and other workers. So now you have that data replicated across. If it's a reliable receiver, this would be your opportunity to say that when these blocks were replicated, you could then acknowledge back to that source system that you process that data and you have it, right? Because when this returns, you're guaranteed that that data is now on multiple nodes and it's been persisted. After that happens, then you return back to the Spark master and to your driver saying that here's the block IDs that I have. Okay, so from that point, it could then schedule jobs to get run. Okay, if we remember, Spark streaming is Spark, most part, in micro batches. Right? Some things are different, but for the most part, it's Spark with micro batches, right? Like a half a second. So there's two ways that we could create a DStream. One, we saw some sort of streaming source, basic, advanced, a custom one. The other is by doing a transformation. Creating a DStream via transformation is really any sort of transformative operation you're doing, right? You can look through the Spark documentation, there's a whole bunch of transformations that you could perform. Map, flat map, and so forth. Right, so you'd have an input DStream, you perform some transformation on it, and you get an output DStream. You can see these general classifications. Just the standard ones that you'd expect to see in Spark, you'd expect to see in other places. Map, count by value, reduce by key, join, and so forth. And then there's stateful operations. Window, update state by key, a transforming one, count by value and window, and some others. And we'll go through a couple of those in more detail. So when you look at transforming input, here we have a stream that we created. It's just called create custom stream, pass in the streaming context. And then we have my stream.map and do whatever we're going to do there when we get back to these events. If this is time running across, or we said at every interval, we're basically producing an RDD, right? So you'd have this batch here at time t, +1, +2. Right, so at every time this runs, you can get your input stream, you can perform your map, and you can get your RDD coming out. And this can happen on every single time that that batch is running. Let's talk a little bit about stateful operations. The first one is update state by key. So this is interesting. It provides you a way to maintain arbitrary state and continuously update it while your job's running. Say you had, in-session advertising, or we're going to track Twitter sentiment, or there's something else you want to do, and you want to have the state around as data's flowing through. This would be a way that you could do it. Two things that have to be done in order for you to take advantage of that. One, you have to define the state. This could be anything that you want it to be. And you have to define the update function. Okay, and your update function is going to need to know how to update the state using the previous and the current. Okay, so it could be your data, whatever you want it to be. Maybe you're tracking visitors or tracking sentiment, and as the sentiment's changing, and you need to have a way that you could update it and pass in the function that's going to perform that operation. The other thing that's required is checkpointing has to be configured. Right, if you think about it, this is keeping state as the job is running, and you're going to want to have checkpoints going, right, so that you don't lose data. Here's an example of using it. Let's say we wanted to do that sentiment, right? We want to keep track of per user mode as state, and want to update it with his or her tweets as they're flowing through the system. So say we have an RDD that's called tweets. We're going to call update state by key. We pass in this function that's going to be update mood, and it takes a tweet. Okay, so update mood is going to take the new tweets and the last mood and produce the new mood. Okay, so you could see as this is going along, each batch here as it's executing, right, we're going to be updating these moods and keeping them. Right, so every batch interval that's running, we're going to have these moods that we're holding on to and constantly updating as it's flowing. The other stateful operation that requires a little more discussion is transform. So transform allows you to do arbitrary RDD to RDD functions on your DStream. So you can really do anything you want. So this transform takes in some transform function that produces an RDD and returning back that DStream. So if you had it, like we say have here, that we want to eliminate noise words from crawl documents, right? Say we sucked in data from Hadoop, we have this noise words RDD, and then we have this crawled corpus that we're crawling, and we want to transform it and get rid of noise. All right, this is a DStream that's here. We're going to call transform on it. For every RDD in that batch, we're going to basically call join on that noise word RDD, and then filter. Right, so you can do whatever you want there. This could be a regular old RDD that you got from anywhere. Okay, so it gives you an opportunity to have historical data that you're combining with a stream. Okay, to note, when this gets called, this gets evaluated, and this join or whatever it is you're going to do here is going to get evaluated on every single batch run. So if you wanted to be updating historical data as the day's going along, you'd have an opportunity to do that here. So you could be updating historical data, you could have a stream going, and you could transform that incoming stream with the historical data, maybe tack onto it. Maybe it's the weather, maybe it's a visitor, something that you want to do and tack onto. And we saw on the previous screen that we had that join that we're using. You could also do a join on two DStreams. The join on the previous screen with the transform, again, is an RDD to RDD. In this case, we're going to join two streams. So say as an example, you have a group of users that are using some Fitbit device and maybe an application like, say, Map My Run. And you have two streams coming in, and both of them have some user ID on them. Then you could call, say, this Fitbit stream and tell it to join with your Map My Run stream. That's going to turn around, and if you have two DStreams, say Fitbit stream has an ID and the data, and let's say the Map My Run stream has an ID and the data, key and the value, what you're going to get coming back from this join is a key that has that user ID that was found in both with a tuple that has the values from each. Okay, so now you've joined those two streams of data as it's flowing. You can't do this with a DStream and an RDD. You have to do transforms that you're looking at each RDD in the batch. Yeah, so after we've ingested data, we've transformed the data, and then we're going to want to output the data. Okay, so let's just say, assume we create this custom stream again, we perform some sort of map, and then we're going to perform some sort of action. Right? If you've used Spark before, Spark streaming is the same way. Right? It's very lazy. Right? It's going to do everything that you do as a transformation as really just a recording of, yep, need to do that, need to do that, need to do that. But nothing really happens until an action is performed. So when we hit this for each, right, we're going to have some action that's performed. So the same thing. We're going across in these batches of time. We're going to be looking at these as RDDs, can perform some map. We're going to go ahead and have this events DStream, and then we're going to eventually do this for each RDD. Thing to keep in mind with that for each and you're outputting data, right? You want to make sure that that's non-blocking and it's performant, because that's going to be writing to some external system, and it's going to start to hold things up if that's not performant. Okay, because that's going to pull in data and start writing somewhere. So this is just a representation of that little Spark streaming job of how you go from this DStream to that Spark job. Right, so we create this input stream, we perform some sort of map, perform some sort of count, and then we have a for each, which is the action. Under the covers, that's going to get converted into a Spark job for each execution of the batch. So you're going to have an action that caused it, that for each. You're going to have the count happening, and you're going to have the map, and you're going to have the input. So in every batch cycle, that's what's going to end up happening. So you go from here to here, and this is what's executing. Let's talk about time a little bit. There's a couple of things that you need to think about when thinking about time. Windowing, which you've probably heard discussed in any of the streaming talks you've been to in the last day and a half. The notion of stream time versus event time, and then how you deal with out-of-order data. There's a couple of common windowing types that you see out there, tumbling and sliding. Spark streaming today only implements sliding windows. Okay, for better or for worse, that's what it has. There's ways to work around some of its limitations, but that's the windowing that's there, and we'll step into that. So let's first look at tumbling, just so we have some perspective of the difference between the two. So in a tumbling window, and this would be like a tumbling count, the window size is fixed, and the data is evicted from the window at a specified size. Right, so if we said here that the window length is going to be, say, 1 second, whatever data came in, that's it. It's ejected. Okay, and that doesn't matter. That's considered the window being full, and the next window. Okay. This is tumbling in a temporal way. And I think I said the wrong thing to you on the slide before. The tumbling count is based upon the size of the window, not the time of the window. Okay, so in this case, say we have a window size of 2. It's going to be 2 elements in the window, and then it'll be a new window that gets created. Temporal windowing, again in tumbling, this is going to be based on time. So we have this being several seconds. It doesn't matter whether there's 3 elements of data or 5 elements of data. You're going to have a window that tumbles at every demarcation of time that was sent. Sliding window is what's provided in Spark streaming today. And the way that this works is you have an overall length of the window, and then you have an interval. Okay, so we may be looking at a window length of 2 seconds, but our sliding interval of when we're going to execute is going to be over 1 second. So you'd see this data for the length of the window, but you're executing in the interval. And in this case, eviction's happening as the data is sliding. Right? So as this window is sliding across and time is continuing to run, then data is going to continue to get evicted. So a little bit different than a temporal way of doing it. There's 2 types of sliding windowing that Spark streaming supports. There's non-incremental and incremental. And there's just a slight twist on sliding windowing. So non-incremental is the easiest way. In this case, we have this reduced by key in window, and we're going to pass in a function that's going to go ahead and aggregate the data, and we're going to tell it that we want a length of 5 and that we're going to run every second. So you can see, as this happens, we're doing interval counts every time, and then we're going ahead and summing them up. Okay, so you can see how that could get expensive over time. Incremental sliding is a little bit more efficient. Right? Instead of having to do the aggregate for the previous time of our window, we're only having to look at that first time and the time we're at now. Right? The caveat is you need to provide an inverse function to be able to do that. Okay, so if we look at this previous slide, right, we just need to provide an aggregate of how to get to this number by aggregating these. But when we have incremental, right, not only do we need to know how to aggregate it, but we need to how to basically, subtract it, right? Do the inverse of whatever that computation is. So at that window, we could go from this value and produce the right sum, right, or whatever the output's going to be. So if you could do it, and if your problem supports you doing that in the data you're storing. That could be a much more efficient way of having the windowing than having the non-incremental. So let's take a moment to talk about stream time versus event time. So stream time, right, is the time when the record arrives into the streaming system. So when Spark Streaming gets the data, that's stream time, right? All the windowing is based upon the time it receives the data. Event time is the time that the event was actually generated, right? So if I have this, smart tag here and it's sending data pulses, when that's getting created, that's the event time. That may end up in Kafka and then getting sucked into Spark Streaming. When it gets into Spark Streaming, again, that's going to be stream time. And you can have the same thing in Kafka unless you set up your data to all go to one partition, right? That the guarantee is all the data is in order in the partition that you're reading it from, but that has nothing to do with the time that your data was actually created, right? So you have the same type of thing. So in the case of Spark Streaming, you're dealing with stream time. So if you wanted to be able to do computations based upon when the event was created, you're going to have to be conscious of that and make sure you're handling it correctly. Because as you're scrolling across those windows of time, it has nothing to do with when you created it. Right? So that's where a tumbling window or other windowing would be able to help, where you could say, you know what, set the window based upon this timestamp in my data, and have the window based upon that, not based upon the time that the data was received into the system. Other thing to think about is out of order data. In some applications, it doesn't matter. In other applications, it's a big deal of whether the data is in order or out of order. Okay, again, this is left up to you to figure out how you're going to handle that situation as the data is flowing through your system. From Spark Streaming standpoint, if the data source you're reading from is providing the data in order, it's in order, right? But it really has no understanding as to what that data is. So here's a way that you could handle out of order data. So say we want to track ad impressions between some time and time plus I, right? You could have this interval count that you're keeping and keeping track of this state, right? So you always be keeping track of what it was. You have this sliding interval here of t+1, t+2. You'd have these interval counts for that time plus 1, right? And you keep that going as you go along. This is based on this continuous analytics over discontinuous streams. So if there's a problem that you need to deal with, that's a pretty interesting paper to take a look at. And you could think of ways that you could apply this to your data by following this and basically keeping the count, the current count, and the previous count as you're going along. Let's take a moment to look at the checkpointing in part of the recovery and fault tolerance. So there's two types of checkpointing that you can turn on in Spark Streaming. One deals with metadata checkpointing, and one deals with data checkpointing. Right, so if we imagine this being our application running, and we're keeping all this state at every time interval, we want to make sure that if something goes south, which it's going to, that we don't lose data. So without having checkpointing, it looks just like we saw on the previous slide, right? We're going along, we have the state that's building up, and if something fails in our application, we're going to lose that state information. When you enable checkpointing, at regular intervals, it's going to write to some resilience store. It could be HDFS, it could be S3, but it's going to write that data somewhere. In the case of metadata checkpointing, we're just writing information about the lineage and just the metadata of what's running. In the case of data, we'll see that we're writing data, okay, so that we know what's being run. And it's a balancing act. If we're writing too quickly to HDFS, then that's going to be a bottleneck. If we run too infrequently, then the lineages that we're building up, right? The RDDs, again, just like Spark, right? So you have this lineage that's building. And you imagine these are running, say, every half second. You got this lineage that's building up over time. If you're not writing checkpoints often enough, then that's going to grow. The default setting today in Spark streaming is a multiple to batch interval that's at least 10 seconds. And the recommendation currently is to have an interval of 5 to 10 times your sliding interval. So fault tolerance. If you're familiar with Spark and all the properties of RDDs, that they're immutable, they're deterministically computed, and they're distributed data set, Spark streaming has all those properties that tag along with it. Right? And there's two things that we're trying to prevent. We're trying to prevent the failure of the worker that's going to have all the data that's there, and we're trying to prevent the failure of your driver that's going to have the block IDs and the lineage information and everything else that's contained, right? It's scheduling the jobs. So we're trying to prevent failure of both of those. Checkpointing provides you a way to do that. It's different semantics that you could achieve as well. We have at most once, right? That at most the data is going to be processed one time, or that message coming through is once. At least once, and then exactly once. Depending upon the data source that you're using and the provider you're using, the receiver, you could achieve different levels of this. If you use write-ahead logging, and you use a data source that allows acknowledgement, like say Kafka, then you could get exactly once. If it's an unreliable, then not, right? The places you'll need to think about it are going to be in your receivers, in the transformations that you're doing, and then in the output. Right? If you spend all this time getting data from, say, Kafka, making sure you're processing messages one time, if your output is not reliable and it can't handle the same message coming multiple times, then it's going to be a problem, right? So there's places to think about it all along the path. So in conclusion, just kind of went over, introduction, just high-level architecture, DStreams, and kind of some under the covers about those. Talked about how we think about time, and then just touched on recovery and fault tolerance. So thanks, and take any questions.